Hi everyone, this is an educational video in exploring the X-ray diffraction using the online simulation platform MyScope. Our group members are Ketakwan, Dinesh, Shinzuru, and Wenminro. As for introduction of XRD, it is a technique used to determine the crystallographic structure of a material based on their diffraction pattern using the X-ray. In order to get an ideal result, the sample usually are required to be prepared in powder form by using the crushing or grinding methods. Several XRD applications including the phase identification, determination of lattice parameter, crystal orientation analysis, and quantitative phase analysis. The operating principle of XRD. So the first one, XRD beams are being generated in an X-ray tube, and then the generated X-ray with a fixed wavelength are then directed to their sample. The sample is then driven at theta angle per minute. So once the incidence X-ray hits the sample, it will create the reflected radiation. The intensity of reflected radiation at different angles are then recorded using the detector and also goniometer. The intensity are measured to distinguish various d-spacing by using the Bragg's law, n lambda equals to 2d sine theta, where the lambda is the wavelength of X-ray and theta is the angle of reflected radiation detected by the goniometer. So by using this equation, we can get the d values, which is the distance between the atoms layer. The intensities need to be further amplified to be projected as an output. So the intensity peaks are then annotated at 2 theta angle as shown in figure 1, the XRD spectrum. The data are then compared to the non-data set of JCPDS to identify the possible matches. So in this figure 1, peak with the strong intensity represent the prominent crystal plane, and the rest of the peak with weak intensity represent the subordinate crystal plane. Lastly, the red line represent the background radiation.
Hello everyone. So after listening to the brief introduction from my teammate just now, right now I'm going to simulate the XRD through this MyScope application. So first of all, of course when coming towards XRD simulator, we need to choose our specimen. So from this MyScope, actually there are a lot of specimen we can choose from here. So for example, I'll take a very simple one, is aluminium. Yeah, so when aluminum is being taken, first of all, these are the image that show here is the image that a XRD machine is being shown. Okay, so first of all, of course, we need to open the door. When opening the door, you can see that the sample is put inside, and then after that, a door should supposed to be closed down. Yeah, as inside will be having the XRD, the X-ray source, that actually quite radioactive when coming towards our human body. So second part, of course, I need to turn on the X-ray tube. X-ray tube, which is important in emitting the X-ray towards the sample. So when I'm turning on, you can see that the voltage are keep on increasing, and same goes to the current. And when coming towards the proof, when coming the power is being turned on, you can see that the full bubble is on. Then we can come towards our scan settings. Yeah, you can see here actually. Yeah, while coming towards our scan settings, why we need to determine the start angle. The start angle determines that how the range of the angle. Yeah, so if your start angle is being set too high, you can, yeah, the start angle and the end angle between the angle, if it's being set too short, it means that your sample result will come out between these two angles only. So for our start angle wise, is recommended to set as low as possible so that a, a broader range of data is able to seen. So if I set here, I just set 5 until 70. And when coming to a step size and scan rate, so step size is what? If our step size is being lower and being smaller, it means that we are having a more precise and also take longer time towards the sample scanning. Yeah, so if our step size is small, so that our sample is being scanned in a longer time. Yeah, so if I want my sample to be more precise, I just choose a shorter one. When coming towards the scan rate, of course, yeah, I need to choose the highest one. Yeah, a higher scan rate shows that actually the sample is being scanned in a high frequency. So a higher scan rate of course will take more time, but yeah, it can also provide you a more accurate and precise data. So after that, yeah, the scan time will tells me the time and then I can start scanning. Yeah, so after I start scanning wise, yeah, you can see that the machine start to operate and here is my data.
My scope is designed to simulate various microscopy techniques, including the electron microscopy, which enables the high-resolution visualization of the nanoscale materials. Second, the fluorescence microscopy, which can be used to visualize the specific molecules via the light excitation and emission. Third, the scanning probe microscopy can analyze the surface by tracing a fine probe across the sample. The platform also incorporates data interpretation tools, which can help the user to understand the imaging artifacts and resolution challenge. Lastly, it provides a risk-free environment for the hands-on training, allow the user to adjust the parameters like the magnification or the beam energy. Score offers the user to gain the foundational microscopic skills, such as the sample preparation, parameter adjustment, and troubleshooting. The simulations allow the experimentation without the risk of the errors which can damage the equipment or the samples. The platform bridges the gap between the theoretical knowledge and the real-world application. It also democratizes the advanced microscopy training, making it accessible to the students and researchers. However, my scope cannot replicate the challenge of the real experiments, such as handling the unexpected sample interaction or the lens aberration. Users cannot predict the actual sample preparation or the manipulation. The sensory feedback, like the equipment vibrations, is absent within the platform. While useful, microscope tool does not substitute for the physical training with the real instruments, especially in the complex scenarios.
Next, I will be explaining the sample analysis using the simulator. As you can see, we obtain the diphothogram of the aluminium. So what the data tells us, the peaks of the graph shows the position, intensity and profile of the width shape. The sharp peaks of the graph shows us the aluminium is highly crystalline material. The sharpness and also the narrow width of these peaks suggest the well order of the atomic planes. Next, the main peaks. The two major peaks are visible in the graph shows the specific Miller indices of the aluminium. The highest intensity of the peaks shows that the planes are most dominant atomic planes in the crystalline structure of the aluminium. The higher the peak, the most prominent that atomic plane is within the crystalline, and the flat background shows that the peak have a low level of amorphous content, meaning the sample is almost entirely crystalline aluminum. And also this data also gives us a qualitative analysis where the use of the XRD spectrum to extract quantitative data such as volume fractions of phases present, the grain size of the sample and also lattice parameters.